Let me start the recording, everybody. This is week 7. We are, I think we're going to look at some questions from chapter 6 and maybe chapter 3 of calculus and algebra. And I've noticed there is some questions about the assignment. I'm happy to talk about that as well. In fact, what I might do next week, week 8, I might turn this tutorial into an assignment tutorial. Okay, so if you feel strongly about that, if you see value or no value, can you let me know in the comment section? Would you see value in having a tutorial on the assignment? Okay. So I know last year what I did was people could share their drafts and they could get some feedback. So I'll do that. All right, 16 people are now very happy to be. Is it due in week 9? I think it's due in week 9, isn't it, Eleanor? Let me just have a look. Let me see when it is due. Assignment due Tuesday, week 8. Okay. Oh, it's a bit earlier than I thought. Yeah. So I guess if we can do it. We can, yeah, well, the Monday still will have some value for you, so it should be fine. I don't know, Steve, whenever they open up the portal, I have no idea. I don't control that. So I'm not sure. Just watch this space. Okay. All right, so let's go and have a look at some of these questions. I think I'll start with inverse functions and then we can talk about some complex numbers. Okay, so let me share my screen. We've got 33 people here, which is great. Yeah. Okay, so I thought I could do maybe a handful of questions from inverse functions, and then I could talk about some complex numbers. Now, there are a lot of H questions this week, harder questions, but usually I do those on the Thursday. So I think I'll save those for the deeper tutorial. So let's have a look at some of these questions. So I thought we could start very simply and look at question 2, and then I might go and do another function, another few questions. Okay, so suppose I've got a function 3x plus 1, find the inverse and sketch the graphs. Suppose I've got a function x squared plus 1, where x is less than or equal to 0. Find the inverse function and the derivative of the inverse. Okay, so it's a pretty much an entry level kind of question. And let me go to my document camera. And we can work through it. So this is question 2 from chapter 6 of the calculus. All right, so let's write down our function. And this is defined for all x. What we can do is we want to find the function that undoes this function. Okay, and so one of the standard ways of doing this is to replace f of x with y, rearrange this to make x the subject, and then relabel everything. So, okay, so now what we've got here, x is a function of y. And what we can do to get the inverse is just relabel everything. So I would relabel this right-hand side where I see y's, I would relabel them to be x's. Okay, so let's just have a look at this because they ask us to sketch the two functions. Let's have a look at that. I can just do that in GeoGebra. So here's our function. Okay, so here it is. And here's the inverse. And here is the line y equals x. So you can see there's some nice symmetry between the black line. That's like a line of symmetry for the green line and the red line. Okay. So that's usually what happens when you have inverses and their functions. You just reflect them in the line y equals x. Okay. All right, so what about part B for this question? Well, I'm glad you asked. So now we have a function which is x squared plus 1 and x is less than or equal to 0. Okay, and so now the question is, how do I compute the inverse? Well, same as what we did over here. Okay, this restriction is going to be important for when we compute the inverse, right? So let's have a look. Let's have a look. So make that the subject. So x is going to be the positive or negative square root, but we know x is non-negative, so we take the negative square root there. Okay. So that this restriction is important because we don't know whether to take the positive or the negative square root. Here we want the negative square root. So let's replace y with x. Okay. And now if you remember, the domain of this function will equal the range of this function. The range of this function will equal the domain of this function. Let's have a look, Abdul Rahman. Let's have a look with this particular question. See if your intuition is right there. You're asking a function and its inverse always intersect on the line y equals x. Let's have a look. So, because we can draw these functions pretty easily, right? So I'll go over to GeoGebra. Did somebody say GeoGebra? Okay, so that is the function x squared plus 1 for x less than or equal to 0. And that's the inverse function. Okay, so do they intersect on the line y equals x? Okay, but they still have the symmetry there. Okay, they still have the symmetry. Can you see that, Abdul Rahman? So the reason is the domain is not letting it touch. Yep. Okay. All right, so last part of this second question, compute the derivative. So let's do that. So we want to compute the derivative of this one. Okay, so here, of course, we want x to be greater than or equal to 1 because that's the domain of the original g function. Okay, so we want to differentiate this. We can do that a couple of ways. One way is to write it like this. You can, if you want to, use the chain rule here. I'm not going to do that. All I'm going to do, bring the half to the front, the derivative of what's in here to the front, decrease the power by 1. So it's going to be negative 1/2 x minus 1 to the negative 1/2. That's it. You could use the chain rule there, but I don't really think it's necessary. Okay, so the half comes to the front. The derivative of what's in the brackets comes to the front. It's 1. You decrease the power by 1. Da, da, da. Big thumbs up. All right, cool. Let's look at another question. What have we got here? What have we got here? Yeah, I'll do one involving sines and sine inverses because sometimes they're a bit crazy, right? So let me go back to my PDF and yeah, here we go. All right, so let's have a look at these sine and sine inverse questions. Now, when students see a question like C, the temptation is to say, oh, sine inverse and sine cancel each other out. But they don't, because 5 pi on 3 is not between negative pi on 2 and pi on 2. So it's important that you think about the domain and the range of these sine inverse and sine functions. So let's have a look at that and see how we can work our way through it. Okay, so this is 8 part C. Part C. So consider, please, sine inverse of sine of 5 pi on 3. Oops, just dropped my pen. Okay, and so the temptation here is that, oh, this cancels out. But the point is 5 pi on 3 is not in this interval. So it doesn't make sense. Okay, so what we would like to do is get this or this into some form where the angle is in this interval. Okay, and so, for example, if I draw a picture where I look at this angle here, that is 5 pi on 3, right? Now that's the same as going the opposite direction with pi on 3. Okay? So one way of doing this problem is to say, right, sine 5 pi on 3 is the same as sine negative pi on 3. And sine is an odd function. I mean, this is definitely in this interval now, right? So if I put that all together, and there may be an easier way to do some of these moves. Right, I just replace this with this up here. And sine inverse is also odd, so I can move that negative sign out there. And now, oh my goodness, we're all lined up. That is in this interval, and it's just going to be negative pi on 3. Now, you probably could have just gone from there, put that into there, and then the signs would have cancelled out. That would have been a faster way to do it. Okay? But the most important thing, I guess, is to see, well, all right, look for when this angle is in this interval for sine inverse. Lisa, like I think what I'm going to do, because this is just a middle of the road one, I think I will save those for Thursday, Lisa. Okay, because that's really what the students that come to those tutorials want. They're the kind of questions that they really want me to do. So yeah, so I'll consider your request, but I can't promise it because this is not really that kind of tutorial, right? This is sort of a middle of the road kind of tutorial rather than a really advanced one. Okay. All right. Let's do one more calculus and then I can shift over to algebra and the complex numbers. All right. Let's go back to my PDF. I might look at this one and maybe this one. Okay. So let's have a look at 11A, and the B and C are very similar. And 12 is an interesting question. It's not a H question, but it's still an interesting question. So I'll do those ones, and then we can switch over to some alg. All right. So number 11. I'm going to let y equal cosine inverse 2x. And what I want to do here, what they're asking us to do, is to compute the derivative. Yeah? Okay. So you can do this a bunch of ways, but I'll do it using chain rule. Okay. So what I will do is move that inverse around and then differentiate both sides. Okay, so that's easy to do, this right-hand side, because the derivative of 2x with respect to x is just 2. This is not so hard, but what I can do is use the chain rule here on the left-hand side. Okay, so watch. Okay, so what I've done there, the dy's can cancel and you get back to the dx, right? So you can just cover these things up if you want to, and you can sort of convince yourself that really it's just d dx. And the important thing here is I can now differentiate this. Okay, that's just 2. So the derivative of cosine y with respect to y is negative sine y. Yeah. So let's move that around, and we can write it in terms of this. Now, that's a perfectly reasonable answer. What some people expect you to do is write this back in terms of x. Okay, so it's not hard to do that, but this is still a reasonable answer. So how do you do that? Well, the way I like to do it is you've got this, and you can write the cosine y is this divided by this. Okay, so let's draw a right-angled triangle where we can use trigonometry. Okay, so let y be this angle. Okay, you can let it be that angle. I'll just let it be this angle. It's 2x divided by 1. So cosine is adjacent over hypotenuse. So that must be the adjacent side. That must be the hypotenuse side. Okay. And now from Pythagoras' theorem, I can get this third side. Okay, it's going to be 1 minus the square of that. Okay. So what I would like to do is write sine y in terms of x's. Okay, so sine y, sine is opposite over hypotenuse. So you can just, it's this divided by this. Okay. So it's quite a long way to do it. The other way to do it is using the chain rule, and other way. Let u equals 2x in star and apply the chain rule. That's probably faster. Okay. All right. So let's have a look. I think we can switch over to complex numbers now. So let's switch over. All right. Now for number 12, let me just briefly show you how to do number 12 before we switch. Okay. So inverse sine plus inverse cosine, prove that it's a constant. Okay, and what is the constant? So how can you do that? Can anyone suggest what you might do in the chat? What might be a strategy for showing a function like this is constant? Who can let me know in the chat? Who can tell me? Week 7. What might be a strategy for this one? Who can tell me? Come on, there's 40 people here. Yeah, Lisa, find the derivative. So if you differentiate that, you get 0. Okay, and then all you need to do is plug in a particular value of x, say x equals 0 or something. Okay, so what you'll get, have I got it here? Yes. So let me go back to GeoGebra and I'll share my screen with you. So here it is. This is the inverse function. Now you can see it actually cuts the vertical axis at pi on 2. Okay, so show that the derivative of these two bits cancel each other out and they add up to 0. And then substitute in x equals 0 into here and you'll get pi on 2. So the derivative. Carl, what do you mean by, I think you mean monotone, right? I'm not sure if the derivative it's not increasing and it's not decreasing. So, you know, I guess the derivative is just 0. Would you agree? Yeah. Okay, great. All right, let's shift over to some algebra. Okay, so is that the algebra? Yes. All right, so it's complex numbers today, folks. So let me just go down and I can go down here. Here are some questions, right? And so what I thought we could talk about are some of these polar forms. Now, if you were in today's calculus lecture, we also looked at things like this through polar forms. So I thought we could talk about this and maybe some of these solutions to the equations, maybe this one. Okay. And then Lisa, we can have a look and see if we can talk about your example as well. Abdul Rahman, there's no, it's not monotone. Okay, so a monotone function is a function whose graph is either increasing or decreasing. Yeah, and this function is neither, right? And the derivative is 0. So that's all that really needs being said about that. So I would not worry about it. It's not. I don't think it's an important part of the solution, if that makes sense. Okay, B, let's have a look at B. So find the Cartesian form of a complex number whose modulus is 3 or length is 3 and principal argument is 5 pi on 6. So this is a pretty standard entry-level question. I always like to draw a picture with these kind of problems because they help you understand what's going on. So let me share my screen and we can discuss this one. So the modulus is equal to 1 and the principal argument is 5 pi on 6. Okay, so why don't we just draw a quick picture? Oh, this will be the real axis. This will be the imaginary axis. Okay, so it's 1 unit away from the origin, and we rotate 5 pi on 6. So we come all the way over here, and it might sort of be out here somewhere. Okay, so that's 1, and this angle is like 5 pi on 6. Okay. So we're asked to find the Cartesian form. So very similar to polar coordinates, we know that the x part is given by this thing here, and the y is given by this. Okay, where this is, I guess this is your theta here. Okay, so this is going to be 1 cos 5 pi on 6. This is going to be 1 sine 5 pi on 6. So sine's positive in this quadrant, and cos will be negative. So this will be negative something like this. So, oh, hang on, it's not 1, it's 3. No wonder I made it was a mistake. Okay, so sorry about that. Just adjust it to 3. And so this will be negative 3 cos pi on 6. And this will be 3 sine pi on 6. Okay, and well, if you want to draw in your triangle, you can. It's very easy. This will be 2, this will be 1, root 3, and that'll be your pi on 6. Okay, so cosine of pi on 6 will be adjacent over hypotenuse, root 3 on 2. And sine will be opposite over hypotenuse. Okay, so what is our complex number? It is, oh, sorry. Ta-da! Yeah. Okay. So it's mostly trig, as you can see from the calculations, right? Right angle triangles, trigonometry, stuff like that. So let's look at a slightly more challenging problem. Okay, I thought we could have a look at, well, I mean, do you know what cosine of 5 pi on 6 is, Abdul Rahman? Not many people do. So the idea is to get this down to acute angles, which you can easily deal with. So offhand, do you know cosine 5 pi on 6 and sine 5 pi on 6? Because if you don't, you might know them, but if you don't, then it's sort of necessary to break them down into smaller, angles that are less than 90 degrees. Does that make sense? Yeah, Aidan, it's a good question. This is the Cartesian form. Right? And so it's a really good question. And the polar exponential form, so if I wanted to write this in polar exponential form, what I would do is, well, it's this, right? So it's going to be 3 times e to the 5 pi I on 6. Okay, so that would be the polar exponential form for this problem. And this would be the Cartesian form. Okay. So you can kind of see this uses lengths and angles. These use sort of your x direct or horizontal and vertical positioning, right? All right, let's look at one more question, and then we can see if we can have a look at what Lisa was talking about earlier. Okay, so let me show you how to solve these kind of problems. Okay, so these are solving and finding the roots of polynomial equations. Okay, so find the seventh roots of -1 and plot the roots on an Argand diagram. Okay, so basically you want to solve z to the 7 equals -1. Now for these kind of problems, the solution methods is usually the same. Okay, and there's a couple of really interesting mathematical ideas there. So let me do this one, and then maybe we can have a look at what Lisa's interested in. Okay, all right, so let's go back to the document camera. So z to the 7th equals -1. Okay, and z is, you want to solve that for complex numbers. Okay, now, what do you notice about this equation? The coefficients for the z's are all real numbers, and that's a real number. Okay, so what we would suggest in the form of our solutions is that these occur in conjugate pairs. Coefficients are all real. And so solutions occur in conjugate pairs. So who can tell me why is that important to know? Can anyone tell me on the chat? Why is this super important to know? Why is that really good? Who can tell me? Why is it important to know that the solutions appear in conjugate pairs? Yeah, Eleanor, can you say a bit more? I think you're on the right track. So what do you mean the other root? If we find one, then the other will be the complex conjugate. Exactly. So we can work smarter, not harder, right? We find 4 of these roots, and the other 3 will be conjugate pairs, right? And one will be real. At least one will be real. Okay. So for this, let's write this in terms of polar exponential forms, right? So if I write -1, where does -1 lie? It's all the way over there, isn't it? So who can tell me in the chat, what is the polar exponential form of -1? Who can write it? What's our angle and our length? Yep, I squared is right, Russell. But more than that, I'm looking for a length, and I'm looking for an angle. Who can tell me? Yep, the angle is pi. I do a half a rotation. And what's the length? Length is 1, right? So if I want to write this in the polar exponential form, I can write it like that. Okay, so you're all correct. Now, these solutions are like Pokemon. You've got to catch them all. So what we can do is write this in the following way. Okay, what that does is it means, well, I can just keep rotating as many times as I like to get back to this position. Okay, and what it means is I can actually generate all the solutions that I need, right? So I'm looking for seven solutions because it's a power 7. Okay, so let's take the 7th root of both sides, and so I'll make a little subscript there just to sort of just say, well, I've got a sequence of solutions here, right? So it'll be E. Let's factor out the pi i's. So I've taken the 7th root of both sides here. So that's the same as, e to the power 1/7 or 1/7 or whatever it is. Okay. Okay, so now all we really need to do is say, okay, well, let's sketch these in the complex plane, and we'll see what we can find. Okay, so we know it's 1 unit away from the origin, so it will lie on a circle. Okay. Okay, so when k equals 0, this disappears, and it will be 1 e to the pi I on 7. So the angle is going to be something like that. So that might be z0. Okay. So Russell, if you don't have this, you don't catch all the solutions. Okay. And if you want to keep getting back to this point, you just keep rotating by a multiple of 2 pi. Okay. Because if you do a full rotation, it's just 2 pi, right? Okay. So for k equals 1, it'll be 3 pi I on 7. So it'll be something like that, I guess. Okay. For k equals 2, it'll be 5 pi on 7. Okay, for k equals 3, who can tell me what's the solution for k equals 3? Who can tell me? It's pretty simple. Who can tell me what is the solution for k equals 3? Let me know in the chat. Smash that chat button. So when k equals 3, what do we get? What's the actual? What will z3 be? Who can tell me what is the actual representation for z3? So the angle is pi, that's for sure. So what will it be? Yep. And what's that, Abdul? Yes, Joyce is correct. It'll be over here, -1. Because you do half a rotation and you go out 1 unit. So that's Z3. Okay. And so the other ones will be the same now. So this will be Z4. This will be, I think this will be Z5. And this will be something like Z6 here. Okay, 1, 2, 3, 4, 5, 6, 7. So we've got our 7 solutions. Okay, and my drawing isn't very good, but all these angles should be the same. Okay, so these are all pi on 7 radians. All right, Lisa, what do you want to talk about? What's your question? I'll consider it and see if I can do it. Chapter 6, 14. Let me have a look. Oh, okay. Let me see if I've got that somewhere. Oh, yeah. Dun, 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 dun. Okay, that'll be good. Let's do 14. So let me go back and just show everyone. Here's one that I've created earlier. I've got a solution for this already. So, draw the graph of cosec x. Show that cosec x restricted to this interval has an inverse function. Sketch the graph of the inverse and calculate its derivative. Okay. So let's see if we can do this in GeoGebra first. Okay. So draw the graph of cosec x. Let me see if I can. I don't know. I'm not sure if we can do that, but let me just plug around here in the background. Okay. Oops. So just give me a second. Okay. Show that cosec restricted to this interval has an inverse function. Okay. So let me I'm just typing some stuff here. So I'll just bring it up in a minute when I've got it going. Okay, all right, good. All right, let's bring that up. Okay, so here it is, people. So here is the graph of cosec x between 0 and pi on 2. Okay, and you can see what happens is the function sort of goes off to infinity as x gets small, and it looks like it's got some sort of turning point at x equals pi on 2. Okay, so the question now is, why does this function have an inverse on the interval 0 to pi on 2? Who can tell me? Lisa, what do you think? Yeah, horizontal line test. It's a decreasing function. Yeah, and therefore it's one-to-one, as Abdul Rahman has said. So it passes the horizontal line test. It's a decreasing function. It's one-to-one, so it's got to have an inverse. Okay. So let me see if, I don't know if Maple will invert this. Oh yeah, it does. Oh, how good is Maple? Is GeoGebra. Okay. So there you go. There's the inverse function. Okay. So you can see the inverse function is reflected in the line y equals x. Okay. Okay, so what happens if you wanted to do that by like hand? I can show you my rough sketch on this. So the way I did it, and these are some that I prepared earlier. So you can see what I did in my notes. I just said, okay, well, cosec is 1 on sine. So I sort of drew the sine function and worked out where it was 0. And then that's the interval that we're interested in. And so for 0 to pi on 2, you get that part of the curve, which is definitely decreasing, and 1 to 1. Okay, let me see if I can zoom in on that. Okay, that might be a bit better. Okay. And so for the second part, what I've done is I've said, right, from the graph, that part, you can definitely tell that the function's a decreasing function, and it must have an inverse on that interval. Okay, so let me just double check that. And I think I've got to open into it. It probably should be closed. Okay. And so what I did then, I said, right, let's look at that and just reflect it in the line y equals x. And these are my sort of, you know, crappy graphs. Okay, so that's probably the argument that they're looking for. All right, folks. Lisa, is that okay? Is that what you had, or did you get anything similar to that, or you didn't know where to start, or? Okay. So there's a couple of minutes now, people. We can discuss the assignment, or whatever's on your mind. Everyone can turn on their microphones or their cameras if they want to. Let me know what's happening. Let me know. There's 41 people here. Almost the same number as the lecture this morning. There were 50 in the lecture this morning. Let me know what's going on. Let me see if I can show you something cute here. Can you see that? It's my dog, my new puppy, asleep. She's sleeping too, right? She's very, very black, isn't she? We lose her sometimes. Hey. So anyway, back to me. Yeah, she's pretty cute. I know, Abdul Rahman. You know, when I was at high school, I wished that I was a pigeon sometimes. I would just look out the window from my classroom and I'd see pigeons just flying around, not caring about anything. And I'm like, you know what? I think I want to be a pigeon. So I understand. Hey, thanks everyone. Good to see everyone again. I hope week 7 is a good one for you. And I will say goodbye. Yes, Steve, it's really bad at night. I end up stepping on the dog every couple of days. It's pretty funny. Yeah, it's hard to find black animals, that's for sure. But I will sign off. So next week I'll try to do a assignment inspired tutorial. Unless you say no, that's what I'll try to do. And yeah, just enjoy the week, and I will see you later. Okay. All right. Fluffy the what is it? A penguin says bye too. All right. Bye everyone. See you.